Hello friends, in this video I'd like to solve the following problem from the International Mathematical Olympiad 2001, which was shortlisted. It's shortlisted problem A4, which was proposed by Lithuania. We wish to find all functions f from the set of real numbers into itself, satisfying this functional equation f of xy times f of x minus f of y equals x minus y f of x f of y for all real numbers x and y. It's a truly beautiful functional equation, one of my favorites. You will see in a moment why, but here are my hints. So first, let a be just f of 1 for the sake of brevity, and set y equals 1 in our equation to show that our function is either 0 or ax. So for every x, either this is true or this is true. And then define set G to be the set of all real numbers at which our function is not 0. And you should show, here comes the beautiful part, that either G is an empty set or G is a subgroup of non-zero real numbers with multiplication. What is a subgroup? Well, subgroup should satisfy these conditions. First, in our subgroup G, 0 should not be in our subgroup, 1 should. If some element is in our subgroup, then its inverse should also be in our subgroup. And if two elements are in our subgroup, then their product should also be in this subgroup. Alright, and then show that the converse is also true. So if we have some set G, which is a subgroup of non-zero real numbers with multiplication, then any function f defined by f of x equals ax for elements of our subgroup and 0 for every other element, every function of this form also satisfies our functional equation. So give this problem a try and I will see you in just a minute. Right, so as I suggested, first, for the sake of brevity, let a be equal f of 1. It's some real number. Now, let's set y to be 1 in our functional equation, which I will mark asterisk. Then we have the following. On the left-hand side, we have f of x minus f of 1, but f of 1 is a by definition. It's x minus 1, f of x times f of 1, but f of 1 is a. Now, let's do some simplification. F of x squared minus a f of x equals a x f of x minus a f of x. And now some cancellations can be noticed. This cancels with that, and we can put everything on the left hand side, we can factorize it, and we'll have f of x times f of x minus ax equals 0, which means that either f of x is 0 or f of x is ax. And let me be very clear, for every real number x, either this is true or that is true. I'm not saying that our function is constantly 0. I'm not saying that our function is ax for every x. No, for every x, one of these two possibilities is true. Let's call this condition square. Alright, now let's take a look. If our function is constantly 0, then it satisfies obviously condition asterisk, because on both sides we have 0. Yes, let's go back. For example, 0 equals 0, no problem there. So now suppose now that f of x is not 0 for some real number x. And moreover, let's define set G, which will be all the elements, all the real numbers at which our function is not 0. Obviously, because we assume that f of x is not constantly 0, we know that that G is non-empty. So we know that, first of all, G is non-empty, and moreover, let's go back to our formula. Notice that a cannot be 0, because if a is 0, then f of x is 0 or f of x is 0, so our function is constantly 0. So and a is not 0. And now I will prove several claims about this set capital G. My claim number one, I claim that 0 is not in our set G and 1 is in our set G. Proof of my first claim. Proof. Well, 0 cannot be in G, because notice that setting x to be 0 in our condition square, and we'll get the following. F of 0 is either 0 or f of 0 is 0. F of 0 is 0, so 0 is not in G. And moreover, let's set x to be 1. Nothing to be said, but notice, moreover, f of 1 is a, and we are assuming that a is not 0. So 1 is in our set G, which closes the proof of my first claim. Claim number 2. I claim that if x is in our set G, then 1 over x is also in our set G. Let's prove it. Let's prove it. Proof. Suppose to the contrary, that G is in our set G, but 1 over x is not. And we will set y to be 1 over x in our condition asterisk, our very first functional equation. And what do we have? On the left hand side we have f of x times 1 over x, f of x minus f of 1 over x equals x minus 1 over x times f of x, f of 1 minus x, 1 over x, sorry. Alright, and now let's take a look. Here we have f of 1, but f of 1 is a, and it's not 0. Here we have f of x, and f of x is also non-zero. Why is that? Well, because we assume that our element x is in set G, which consists of every x whose f of x is not 0. Moreover, f of 1 over x, since we are supposing that suppose that, to the contrary, that 1 over x is not in our set, so f of 1 over x is 0. And here it is 0. So we have this equation. F of 1, which is a, times f of x equals 0, and here is the problem because it's not 0. and this is also not 0. So contradiction, we get contradiction. Contradiction, which means that for every x in our group, 1 over x is also in our set, is 1 over x is also in our set, which closes the proof of claim number 2. Claim number 3. Claim number 3. If x and y are in our group, and if x is different than y, then their product is also in our set. Let's prove it. Proof. By our equation, let's just take a look at our functional equation. F of xy, f of x minus f of y equals x minus y, f of x, f of y. Yes. Now let's take a look. We are assuming that f of x is not 0, f of y is not 0, and we are assuming that x and y are different. So this is also not 0. So the left-hand side must be also not 0, which of course means that f of xy is not 0, i.e. xy is in our set G, which closes the proof of my third claim. And my last claim, what about two elements which are the same? Claim number 4, if x is in our group, in our set, I claim that x squared is also in our set. Proof. Again, let's suppose to the contrary. Suppose to the contrary that x squared is not in our set G. By claim number 2, we know that 1 over x is in our group, in our set rather. And let's take a look at our equation and now set or maybe change. Let's change x to 1 over x and set y to be x squared in our condition asterisk, in our very first functional equation. Then we have the following. F of xy, but xy is 1 over x times x squared times f of 1 over x minus f of x squared equals 1 over x minus x squared, f of 1 over x, f of x squared. And now let's take a look. Here we have this part right here is f of x, and f of x is assumed to be not 0. F of 1 over x is also not 0. F of x squared, we assume that it is 0. And here we have f of x squared once again. So we have this equation. F of x, f of 1 over x is 0, and we have a contradiction because once again this is not 0, this is not 0. Contradiction. Once again, which closes the proof of my final claim. And now, as a consequence of these 4 claims, corollary, we can say, corollary of these claims, G is a subgroup of the set of non-zero real numbers with multiplication. How do I know it? Well, let's take a look. 0 is not in our group. It isn't. So, well, 1, which is the natural element of multiplication, is in our group G by claim number 1. It is. If an element is in our set, its inverse is also in our set. It is because of claim number 2. And if I have two elements, and if I multiply them together, I am yet once again in our set G. It is true by claims number 3 and 4, because claim number 3 was about product of two different elements, and claim number 4 was about product of the same two elements. Yes. All right. So we have established. Maybe let's write it. We have established that if our function is not constantly 0, if f which is not constantly 0 satisfies our equation asterisk, then f of x equals ax for x's in our set G, and is 0 for x's which are not in our set G, where a is some real number but not 0, and G is a subgroup. Is a subgroup of R star. Now, to finish my problem, I will show that the converse is also true. So if I have any function of this form, it also satisfies my equation asterisk. We will prove the converse. So to do that, suppose that A is some non-zero element and G is a subgroup. It's a subgroup of R star, and F of a set of real numbers into itself is given by our equations. So it's either ax if x is in G, and it's 0 if x isn't in G. I wish to show that this function satisfies my functional equation. And to do that, I will consider three cases. Case number one, when I have two elements which are in our group G. Two elements which are in our group G. Then let's compare left-hand side and the right-hand side. On the left-hand side, we have f of x, y, f of x minus f of y. Maybe let's write that then, since our set G is a subgroup, xy is also in our subgroup, and, well, since it is in our subgroup, f of xy is axy, f of x is ax minus ay, and that can be written as a squared xy x minus y, while on the right hand side we have x minus y, f of x, f of y, which is x minus y, ax, ay, which is a squared xy, x minus y. Exactly the same. Second case. Case number 2, when both elements are not in our set G. It is actually very easy, because then on the left hand side we have f of xy, f of x minus f of y. And what is that? Well, since both elements are not in our subgroup, this is 0, this is 0. So the entire left hand side is 0, while on the right hand side we have x minus y, f of x, f of y. Well, This is 0, so it's also 0. Left-hand side is once again equal to the right-hand side. And finally, the mixed case, case number 3. For example, x is in our group G, but y isn't. Well, notice that then, first of all, xy cannot be in our group. Let's prove it real quick. If x is in G and xy is in G, then, well, 1 over x is in G because it's a group, and y, which is equal to xy times 1 over x, is also in G, which is contrary to the supposition that it isn't. So this little explanation shows that xy is not in our group. And now let's consider the left-hand side. On the left-hand side we have f of xy, f of x minus f of y. We know that this is 0, so the entire left-hand side is 0. And the right-hand side, x minus 1, y, f of x, f of y. Well, since f of y is 0, this is 0, so once again, it's 0. And you may wonder about the fourth case, when x is not in G, y is in G, but there is no need to consider fourth case, because notice that we can change these two elements and these two elements, and we can reduce fourth case to the third case. So there is no need to consider fourth case. Which means that our functional equation is in fact verified, which allows us to write our solution set. So solutions of our equation: f is either 0 or f of x is ax if x is in G, and it's 0 if it isn't, where a is some non-zero real number and G is a subgroup of G. And that closes our problem. But maybe make this ellipsis smaller. Alright, that closes our problem. A very nice problem. It's a bit unusual to involve group theory in functional equations, but it's beautiful. I really enjoy this problem. It's one of my favorites. Sadly, this problem was considered to be given on this International Mathematical Olympiad 2001, but in the end it was not given. Probably it was considered to be too non-standard, even for IMO standards. So let's go back, and once again it was proposed by Lithuania. So very nice problem, truly beautiful problem from Lithuania. So once again, our solutions are indexed by subgroups of the set of non-zero real numbers, and that closes our problem. So thank you very much for watching. I hope that you've learned something new this time, and I will see you next time. Goodbye.